Welcome to the GE Digital Energy Learning and Development channel. This presentation will provide an overview of the Universal Relay version 7.3 firmware. The phones will be muted until the end, where we will open the phones for a question and answer session. This presentation has been set up as a training module. As per all our training modules, we want to measure your success, and a short quiz will be provided at the end of the module. We are setting standards and guidelines to ensure that the learning experience is the best that it can be. Our agenda for this session will be: what is 7.3, and what are the changes in protection functionality, and what are the changes in communication functionality. At the end, there will be a live demonstration on the setup and configuration using a new firmware. So let's get started. UR firmware version 7.31 was released on February 5th, 2015. It introduces a brand new 61850 implementation that enhances the IEC 61850 capabilities to the UR family of devices, as well as specific new PNC functionalities. Let's go ahead and review the next part. From a protection perspective, only the bus differential protection elements were impacted. The B30 now supports power and energy metering. The B90 now supports up to 6 bus differential zones. Let me elaborate on each one. The B30, what this means is the power and energy metering are now part of the actual values and analog operands. Now let's keep in mind that the voltage inputs need to be configured for the power and energy values to be available. So this eliminates the need for external power and energy meters on a small bus bar application. In the previous firmware version, the B90 had only 4 bus differential zones. In version 7.3, the B90 now has 6 single-phase differential zones available in one device. Now, if you ordered a B90 with the 4-bus differential zone option in a previous firmware version, and you upgrade to version 7.3, you are automatically upgraded or receive 2 additional zones at no charge. So the benefits of this: it reduces the number of bus bar protection devices required to protect a small split bus bar. The new communication functionality focuses on the implementation of IEC 61850 Edition 2. It includes standard 61850 system configuration language files such as CID, IID, and ICD files. We'll discuss the role of each file type. There's a list of extended mappings of elements within the UR relay for 61850 Edition 2 as well. There are configurable data sets that are used in Goose Messaging, buffered report control blocks, and unbuffered report control blocks. The BRCB and URBCB now support 5 simultaneous clients. There are now 6 fixed logical devices instead of 1. We've made some changes in the Goose priority and Goose revision portion of this, so we'll review this list in detail. The settings in the relay are divided into 2 sections: public and private sections. The difference between the two is that the public section refers to IEC 61850 related settings such as Goose, report control block, the server, etc. Public elements are precisely defined in section 6 of the standard. These elements are expected to be understood and allow modifications by all IEC 61850 configuration tools. The private sections refers to everything other than IEC 61850, such as protection and control. It is not defined by the standard. Only the owner's tools are allowed to modify a private element. There are 3 file extensions: ICD, CID, and IID. We'll first look at the ICD. The ICD is the IED capability description file, and it's a station configuration language file that describes a UR with a particular order code, data attributes, control blocks, and factory default values. It contains both public and private sections, and can be copied directly from the UR device or from the University UR setup. The CID, the configured IED description file, describes the required settings of an IED and is intended for transmission of configuration from an IED configurator tool to the IED. The CID file can be part of a SCD file, which we'll talk about next. When importing an SCD file, the InterVista UR setup strips out the UR relay portion and creates and sends a CID file to the UR device, when IEC 61850 settings are involved. The CID file includes all data attributes of the target ID, the control block information and settings, and completely reprograms the receiving device. It will also accept a CID file from a third-party configuration tool, provided that that CID file is derived from a UR ICD file and contains the elements of the ICD file. When a UR relay receives a CID file, it will reboot as well. The SCD file, the System Configuration Description file, describes the complete system configuration, including the single line diagram, all the IEDs and their information models, and the data flow between the IEDs. It is intended for configuration exchange from the System Configurator tool to each one of the IED configurator tools. Typically, a System Configurator tool creates an SCD file by merging an ICD file from each IED in the substation, then configuring or mapping of the Goose message and report control blocks. InterVista UR Setup accepts the SCD file, saves the setting for any UR relays as a URS file. InterVista UR Setup can then send the settings in these URS files to the corresponding UR devices. The IED file, the instantiated IED description file, describes a specific IED to a system configurator tool, typically more or less as configured for its role in a system. The IID file includes the data attributes of the UR device, the control blocks and settings, with all the settings values as they were at the moment that the IID file was generated. A copy of it can be obtained directly from a UR device or from InterVista UR Setup. The IED files can be read in the online window and created in the offline window. From the online window of the InterVista UR Setup program, we can read the ICD and IID files from the UR relay. We can import SCD and CID files from the offline window. Each time a 61850 configuration is saved, it sends a CID file to the relay. The UR Setup program can create ICD, IID, and CID files from the offline window to be used in station configuration language tools. It still maintains the original functionality of configuring and editing PNC settings and configuring and editing 61850 services. The UR relay will accept CID files directly from third-party 61850 configuration tools if the original CID file was created from the UR ICD file. The UR Setup program can import an SCD file from a third-party 61850 configuration tool and strip off the UR portion and write the CID file into the relay. There are 6 logical devices now: master, protection, control, system, metering, and general. The master contains the communications including Goose, reports, remote I/O, direct I/O, virtual inputs, Modbus, DNP, and so on. The protection controls just that, all the protection functions. The control contains control and monitoring functions. The system contains power system devices such as breakers, switches, current transformer, voltage transformers, and so on, including interface to these such as the AC inputs, the contact I/O, the transducer I/O, and hard fiber I/O. Metering contains metering and measurements other than the PMU, including signal sources. General contains flex logic, virtual outputs, non-volatile latches, flex elements, records such as oscillography and data logger, security, front panel, and a clock. A large part of the change in this firmware version is the mapping of PNC elements to logical nodes. In version 7.3, approximately 80 of the 120 PNC elements are mapped to logical nodes. So here's the list of the elements that are currently mapped. Here we have the first 50, and then the next slide. In the logic notes, we not only map the mandatory objects, but we also include the optional data objects, the data attributes as well. This means that every parameter and feature available in the relay is now mapped. The comprehensive and self-described data makes it easier to integrate the IEC 61850 services such as reports, Goose, and client server. So a little overview on what the difference between a data object and a data attribute is. The data object provides information on the origin of the Goose messages UR devices are subscribing to. The data attributes identify the specific remote data point that drives the Goose input pertaining to the Goose control block. So as a result, end-to-end Goose subscription mapping information within CID files simplifies understanding of the Goose service with other devices and integration efforts. This is critical considering growing demand of Goose services in station lands that may have hundreds of remote devices communicating via Goose. Let's discuss the buffered and unbuffered report blocks. There are 12 data sets that can be populated with any IEC 61850 data object and or data attribute. There are 20 buffered report control blocks and 14 unbuffered report control blocks. Any data set can be used simultaneously by any number of TX Goose elements that's used for publishing, or by any number of configurable report elements. Up to 5 clients can establish a connection with the UR relay. Each client can establish a one-to-one connection with one report. In other words, each report can only connect with one client or one client per report. Each client can communicate with a maximum of 4 reports. As mentioned before, there are 12 data sets in the UR relay. Each data set has as many as 64 members. The UR setup requires that data set members consist of IEC 61850 data objects and or data attributes. The data set allows for a client to get the values of all members of a data set with a single request rather than having to individually request each member. Data sets are also used to define which data attributes to include in a Goose message, or a sampled value message, or a report. The data sets are configured so that any 4 data sets can be used for report control blocking. The remaining 8 data sets are allocated for Goose publishing. The UR setup can also configure any flex logic and any flex analog operand as members for the data sets. Here's a table that lists the differences between version 7.2 and 7.3 firmware. The number of data items per dataset, Goose subscription, better known as GGIO 3 in previous versions, had the quantity of data points changed from 32 items in version 7.2 to 64 items in version 7.3. The number of remote inputs changed from 64 in version 7.2 to 128 in version 7.3. A dynamic quality of service was added, and the number of logical devices increased from 1 in version 7.2 to 6 in version 7.3. The number of configurable data sets for reporting services increased from 1 in version 7.2 to 4 in version 7.3. The number of simultaneous buffered report control blocks available increased from 5 in version 7.21 to 20 in version 7.3. The number of simultaneous unbuffered report control blocks available increased from 9 in version 7.21 to 14 in version 7.3. Setting file types were introduced via XML, changed from URS in version 7.21 to SCL in version 7.3. In version 7.3, the settings files used were standard 61850 extensions, .icd, .cid, and .iid. The open transfer services supported for settings in version 7.2, there wasn't any. In version 7.3, we're using SFTP and MMS. And the open file transfer services supported for records in version 7.21 was TFTP, and in version 7.3, TFTP, SFTP, and MMS. In the setup and configuration portion, our agenda will be the following: a review of the new IEC 61850 protocol panel, which has a new layout and operation We'll do a live demo of step-by-step procedure of publishing and subscribing using digital signals. Next, we'll do a live demo of step-by-step procedure of publishing and subscribing to analog signals. So let's begin with the IEC 61850 Protection Protocol panel. The 61850 Protocol panel can be accessed through Settings, Product Setup, Communications, and then finally IEC 61850. The 61850 Protocol panel can be accessed either in the online window or the offline window in the InterVista software. Version 7.3 uses edition 2.0 SCL. As a result, GSSE, Fixed Goose, and Fixed report services of previous releases are no longer supported. Unlike other UR settings in version 7.3, the IEC 61850 protocol configuration settings cannot be accessed through the UR front panel. These settings are accessible with the InterVista software via the MMS query, read and write services, or via the 61850 substation configuration language file transfer. Now, when the Save button in the online IEC 61850 window is clicked, the UR setup software prepares a configured ID description file known as the CID containing all the device's settings and sends the CID file to the connected UR relay. On receipt of a CID file, the UR relay checks it for correctness, and if no error is found, reboots the UR relay using the setting in the CID file. The UR relay displays a message when the UR relay is running the new settings, confirming successful transfer. So this takes a minute or so, please be patient. So the first thing we'll look at in the panel is the server configuration. The server configuration panel contains the IEC 61850 settings relevant to the server functions of the IED implementation. The value entered sets the ID name used by IEC 61850 for the UR relay. For example, we can put in something like feeder A. An IED name must be unique within a network for it to operate properly. You can use uppercase and lowercase letters, you can have digits, and the underscore character. The space character is not allowed, and the first character must be a letter. The next thing on the list are the logical device names. There are 6 of them: master, system, protection, control, metering in general. And the setting allows you to change how the logical devices will be represented. Once again, the name needs to be unique within the network and must be entered for proper operation. The logical device name can be product related or function related names. If these fields are left blank, then the logical device name uses the ID name field left at the top. The location field allows the user to declare where the equipment is installed. The latitude and longitude fields declare the geographical position of the device. So positive latitude numbers are the northern latitudes, the negative numbers indicate southern latitude, positive longitude numbers provide an eastern longitude, while negative longitude numbers provide a western longitude. The altitude of where the device is located can be added as well. Prefixes can be assigned for the GGIOs. So we see listed here GGIO 1, 2, and 4. We'll talk more about those later. The next group of fields is for revision control. Any changes made to that specific logical device will automatically advance the revision. The next field is llno.mod.ctl model, which specifies the control service the clients must use to control the test mode function of the UR relay. The next one is IEC MMS TC port number. This is just leave it at default. This is typically not touched. Now the last one is the configuration type. The choices are either G2 or E3-2.0. Now, E3 is unique to the Spanish electricity company, so they can comply to the standard using 61850 Edition 1 standards. Without going into a lot of details, the difference between the two is that there are some data objects in the LGOS logical node that's unique to each configuration type. So what we're doing is both types of LGOS logical nodes are included in the ICD files when the settings are being saved. The next thing we'll look at is the Goose access points. The version 7 CPU module has 3 ports. Here we can enable the ports that will be designated for Goose messaging. If any of the ports are disabled, the Goose messages coming through those ports are ignored. The update time, as before, is the time interval between heartbeat messages. And of course, these are the messages that are sent periodically while no events are detected. Now, the setting for this, as per the standard, this time should be half of the time to live parameter that's in the TX Goose, which we'll look at next. Okay, next we'll look at the TX Goose, which is the publishing Goose. There are 8 TX Goose messages available. As in previous versions, Goose 1 and Goose 2 are known as the fast Goose, designated for mission critical digital signals only. Goose 3 through 8 are known as the slow Goose, used for non-mission critical signals and analog signals. Next, the Go ID is the name of the Goose message that needs to be unique within the system. So in our network, each Goose message has to have a unique name. Next, the DAT set allows us to select one of the 12 predefined data sets. The DST MAC, the destination MAC field, requires that the multicast bit be set to true. In other words, the second digit has to be an odd number. The VLAN priority has expanded. It's still 0 to 7, where 7 is the highest. A dynamic range has been added so that the first event has the priority value, the first digit, and the next event message uses the next decremented value. So let me give an example. One of the choices are 7-5. So what that means is the first event goes out with a priority of 7. The second would have a priority of 6. The next would be 5. Then the next one would be 5, and then so on. So the standard indicates the priority for Goose messages should be in a range of 4 to 7. I'll skip the VLAN portion. The next part we'll look at is the E-type app ID. The standard strongly recommends changing from the default value of 0. There is a range for type 1 fast messages and type 1A trip messages. So that should be changed. The retransmission time works in this manner. When a member value changes, 4 event transmissions are sent in this interval. So it starts it off with the retransmission time, then on the next interval, 2 times the transmission time, and then on the 4th one, it goes to the heartbeat. The next part is the time to live. The time to live refers to the amount of time for a subscriber to wait for a Goose message before declaring a communication failure. Okay, now let's go over to the subscription side. This is the RX Goose messages. There are 16 RX Goose elements. Let's review each section. First, we'll start with the ID. So the ID is the name of the Goose message that we're subscribing to. The destination MAC should be the MAC address of the publisher. If you have all zeros, this will disable the RX Goose. The application ID needs to match the publisher's application ID. Now here comes a tricky one. This is the GOCB reference. This is the Goose control block reference. This cannot be left empty because this will also disable the RX Goose. So we need to include the GOCB REF field of the incoming Goose message. And this whole name includes part of the logical device name, the logical node 0, and then the Goose control block name. So there's a really unique naming convention used here. In my example, master has a prefix of either the master function ID or IED name. So depending on the programming in the server configuration of the publisher screen, this is the word that we're going to put in front of the master. This is then followed by the /LLN0.GOCB01. Okay, so we got to keep that naming convention. It's very important that we get this right. All right. The next part we'll look at is the dat set. It's the name of the data set used by the publisher. So when we get into that portion of it, I'll talk more about the naming convention for the data set. In the member portion, we need to indicate the type of data that's located in each position of the Goose message. So here's some examples I put down here. So we've got Boolean algebra, Boolean used for the digital signals. We have float 32 used for metered values. We've got integer 32 used for deadband, timers, clocks, and etc. And we have the DB-POS. This is called double bit position. So it allows us 4 possible states. For example, things like bad, interim, on, and off. And then the other 2 choices that we have are the quality bit and if it's a timestamp. Next we'll look at the RX Goose Boolean inputs. This portion in previous versions, in my opinion, reminds me of the remote input designation. There are 120 Boolean inputs available to be programmed. The ID allows us to label this Boolean input. The RX Goose gives us a choice of selecting between the 16 RX Gooses that we want the specific signal from. The member, this is where we select the member number within the Goose message. Remember, there are 64 members per Goose message, so we have to tell it which one we're interested in there. In the default state, we can program the default state for off, on, latest off, and latest on. And we can also record in the event recorders to transition from 0 to 1 or 1 to 0. So these are the type of inputs that we can use for programming in the flex logic. The next thing we'll look at is the DPS inputs. These are the double point status. There are 5 double point statuses to program. These settings allow the user to assign descriptive text to the name of the 4 RX Goose DPS1 flex logic operand. So we'll just go through it quickly again. The ID is the name of the device, so typically being a breaker or a switch. The RX Goose, you select one of the 16 RX Gooses. The member, of course, the selection of one of the 64 members from each one of the Gooses. The default state, we have some choices here. So because it's a double point status, we're looking at 4 different states. So the default states gives a selection of intermediate state, off, on, bad state, and the latest. Now, in your programming, if you make a mistake and you select a member number that is not a double bit position, the signal will assume its default state. Okay, so, and then the last part, of course, is the event recorder. Changes in the Goose signal can be recorded in the event recorder. Okay, now, one more thing. The operand name is the ID appended with one of the 4 signals. So in this case, RXG DPS1, and then it would be appended with intermediate, on, off, or bad. Next, we'll look at the analog inputs. There are 32 analog inputs to program. These can be used as flex analog operands and flex elements. So we'll just go through the screens again. The ID can be changed here, but from the flex elements, it's still referred to as RX Goose analog 1 to up to 32. Okay, so that still doesn't change. The RX Goose, once again, is the number of the Goose messages that contain the analog signal. The member is the location of the analog signal within the Goose message. The operand expects a float 32 result. If the operand is not, then it assumes a default state. Okay, now the default state is when connectivity is lost. This is the value that it shows. So in this case, we're looking at a value of 1000. In the default mode, once again, this is used when connectivity is lost as well, and we have a choice of which value to display, whether we want the default value or the last known. And the next one is that we'll look at is units. The units is a 4-character field that represents the units. And then the last one is the per unit, and the per unit allows us to rescale the per unit base value on an analog value. Next we'll look under reports at the buffered reports first. As mentioned before, there are 20 buffered reports where each one of them has one-on-one connection with the client. The buffered report elements queue values changes that occur while the client is offline and deliver when the client reconnects. Up to 512 events can be queued. Buffered reports are more suitable where the client is using the data for historical purposes, such as, for instance, creating a load profile. In these applications, the events during an interruption are necessary to prevent gaps in the history. So, the first field we'll look at is the report ID. It allows each report service to be given a user-specified functional name. The dataset identifies which of the 12 datasets will be used to create the report message. The configuration rev is automatically updated when changes occur in this screen. The optional fields is a bit string that controls which additional fields are included in the report. So you can see here the choices are things such as sequence number, report timestamp, reason for inclusion, data set name, data reference, buffer overflow, and entry ID. The buffered report time is the interval time in milliseconds for the buffering of events for inclusions in a single report. In other words, how long after initial event to collect and append possible additional events before sending a report message. The trigger option is a bit string that controls which trigger conditions are monitored in this report. In other words, what condition will generate this report. The options are data change, a quality change, integrity, and general interrogations. The last setting on this page is the INTG-PD, which is the interval of periodic reports. So the question is, how often is this report being sent, whether a change has occurred or not. And this report time is in milliseconds. Next we'll look at the unbuffered reports. As mentioned before, there are 14 unbuffered reports to choose from. Each unbuffered report has a one-to-one connection with a client. Unbuffered reports are more suitable where the client is just displaying the reported values or using them to make real-time decisions such as a tap change or voltage control. Now, in these applications, events during the interruption are not of interest. The configuration screens, as you can see, are exactly the same as they are in the buffered reports menu. Next, we'll look at the data sets. There are 12 data sets that are shared between the reports and the Goose Messages. 8 are assigned for Goose Messages, 4 are assigned for the reports. Each data set has a factory default name associated with it, or you can rename it. This is the dataset name you're going to need to reference when you're programming the subscription portion of the IEC programming. The naming convention has to follow the IEC 61850 standard, which consists of uppercase, lowercase, digits, and the underscore character. Now, every dataset has 64 members or data points. If you go into each member, you'll see each signal in the pull down falls into one of the 6 logical nodes: master, protection, control, system, meter, and general. Next, we'll look at the categories under product setup. The first one is energy. There are 4 energy sources, and this is associated with the number of DSP modules. There are 2 sources per DSP module. So this is where we set up the deadband for the energy. The deadband represents how much the analog value needs to change by to trigger a Goose message or a report. Next, we'll look at the signal sources. This is where we find deadband configuration for our metered values. MMXU refers to source 1. Under source 2, you'll find logical node MXU2, and so forth, so on. In previous versions, the sources were located on one screen. Now each source has its own menu. Different meter values have different references for the deadband percentage. For example, the phase current has a reference of 46 times CT primary, and phase-to-phase voltage is 275 times the VT ratio setting. So you need to check the manual for what the references are for each parameter. Next, we'll look at breakers. The difference in this version is that we separated each one of the breakers into their own menu and added some security for control. So an additional logical node, CSWI, has been added for remote open and close operation of each breaker. Next, we'll look at the switches. Once again, we separated the 16 switches into their own menus, which made it much easier to read. We added interlocks for open and close operations controlled by flex logic operands. And we've also added security for control and added timers to select before operate, SBO, and operation timeouts. Next, we'll take a look at the flex logic. Under flex logic, we have flex elements. The flex elements now have their own logical node. And here we can set up the deadband for the flex element operand for Goose and reports. Grouped elements vary between the different application types. Here we can see the setup for deadband for protection elements such as the restricted ground fault, the sensitive directional power, the watt metric ground fault. On the transformer ones, we can also see percent differential. So this one here is the restricted ground fault, the sensitive directional power, and the next one is the watt metric ground fault. The settings group under control elements is used to select which group will be initialized during the power up. The active settings group can be selected via MMS commands under select active SG. Under control elements, these also vary with the different applications as well. So things such as synchro check and frequency rate of change, this is where we set up the deadband configuration for those as well. So here's the one now for synchro check, and this is what the frequency rate of change looks like. So each one of them has their own logical node associated with it. Next, we'll look at the settings for commands. The UR implements a number of clear record commands. Several of these commands can be issued via 61850. So this screen provides the security associated with the clear records menus such as clear fault report, clear event records, clear all relay records, force trigger, clear oscillography, clear data logger, and clear energy. Next, let's look at the GGIO section. Under GGIO 1, we still have the classic 128 indications, but there's a twist. You can enter a digital signal in indicators if the signal has been assigned a data attribute. If you proceed to cheat and enter a signal that is associated with the factory assigned data attribute, the Goose communication will be unsuccessful. So one of the things that you need to do is you need to check the manual for signals that you're using. If they're mapped, you can't place it in here. If it's unmapped, you're more than welcome to use the GGIO 1. Next, we'll take a look at GGIO 2, a virtual inputs control model. There's 128 virtual inputs that are controlled by IEC 61850 commands. So this setting selects the control model that clients must use to successfully control the virtual inputs. The last thing we'll look at is the GGIO 4, and this is a UR feature that allows any of up to 32 UR flex analog operands to be user mapped to an IEC 61850 model data attribute. Those flexed analog operands that have not yet been factory assigned to a data attribute can be user assigned to a GGIO 4 data attribute. You will need to check the manual to verify which signals are not mapped. If you use a factory assigned data attribute in GGIO 4, the Goose communications will not be successful. Okay, so this concludes the review of the IEC 61850 protocol panel in the InterVista software. Next, we'll go through the steps of configuring a Goose message between two relays. In the first demo, we will configure two UR relays. One to publish 3 digital signals, the contact input, virtual input, and the phase instantaneous overcurrent, and the other to subscribe to these digital signals. The digital signals have been enabled and advanced. The UR relay connections have been named as publisher and subscriber to make the demo easier to follow. The IEC 61850 protocol panel is available in InterVista software from both the online window and the offline window. We'll be working from the online window, so let's begin with the publishing side. So since we're going to be working from the online window, I'm going to turn off the offline window. Here are my two connections. the publisher and the subscriber. I've colored them so one's black, one's blue, so we don't get them mixed up as well. So one of the things that we'll do in here is, I want to show you the device definition of both relays. So they're both feeders, running version 7.3. Okay, so now what we're going to do is we're going to begin with the publisher to find the 61850 standard protocol. The panel is under product setup, communications, IEC 61850. So the first thing we'll do is we'll go into the server configuration. We'll give this a name. I'll call this feeder underscore pub. So this will be our publisher. And this is important because we need to know what this name is. If we're not going to put in any functional names for the logical devices for the different logical nodes, then we're going to be using this as a reference. If we put in a name in here, then we're going to be using that. So we'll just keep it simple. Now, up here, let me explain these buttons up here. The save, once we click on save, it's going to generate a CID file and it's going to reboot the entire relay. So the save button is only selected at the end once you've populated all your other screens. The reset is just that, to reset the settings. The reset will reset everything in this menu. If you just want to reset or clear a specific screen, then you can select default. And of course, if you've accidentally cleared a screen that you were interested in, you can press the restore and it'll bring everything back. All right, the next thing that we'll look at here is, let's go in and let's populate the data set. So down here is our data set. So there's 12 data sets. We'll go into the first one. We're going to give this a name. We're not going to leave it at default. We'll actually give it a name of, feeder underscore pub underscore DS1. So this will be data set 1. We're going to enter in the devices, or 3 digital signals that we're going to be publishing. The first one is our contact input, and this is located under system. So if we scroll down here, you can see that there's a lot of different devices that are available to us. So I know that the signal name is this, system dot contact input GGIO 1 dot status dot indicator 101 dot, and I want the status value of that. Now, why 101? The way this works is, when we're in this in the system logical device, the 101 is code for the first card is the first one, and 01 indicates the first contact input from module 1 that's in your relay. Second thing we're looking at is the VI virtual input. So this is located under master, and it's a GGIO 2. And we're looking for 01. We want the status value of that one. And the third one that we're looking at was the instantaneous overcurrent. That's located under protection. That's perfect. Okay. Now, so this is going to be our data set. These are the 3 signals that we're going to be publishing. Next, let's go back to the Goose. So this is where we can enable the ports, the 3 ports on the back of the relay, which one's going to be related to Goose. I'm going to reduce this update time. This is the heartbeat. I'm going to change it from 60 seconds down to 1 second for our demonstration so that we can see things occurring much faster. And now we're going to go into the publishing Goose. This is the TX Goose, our publisher. And here we're going to go in, and it's already enabled. This is the name of the Goose message. Each one of them has to be unique. So once again, I'll call this feeder underscore publisher, just to give it a name. Under dataset, we're going to be selecting the first dataset. We'll leave the destination MAC alone. The VLAN, I'll put in a VLAN ID and an E-type application ID. And the rest of it I'll leave. And that concludes the publisher side. So we'll click on Save. The relay is actually going through a reboot sequence. So when we save it, it actually creates a CID file, which in turn, when the relay receives that CID file, it forces it to reboot. Alright, now the publishing relay has been updated. Now we'll move on to the subscriber side. Now we'll work on the subscriber side. I'm going to minimize this so this is still available to us, because there are certain screens that we're going to need here. So I'll open up the subscriber side. So here's my second relay. Once again, go into settings, product setup, communications down to 61850. Alright, so we'll go into the server configuration. Once again, it's got a default name, a template. I'm just going to go ahead and change this so it's unique. And we're going to go straight into, we'll go into the access points again. Let's change the update time, because this is for transmission. We can ignore this for right now. For the subscription side, we have these different screens. First things first, we'll go to Goose 1, and the first thing it wants to know is what's the name of the goose that we're expecting. So in this case, let me just bring this back down. The goose that's being published is this one right here, goose underscore pub. We'll copy it over. The destination MAC is this address here. The type app ID from the destination is 1. Now, this is where it gets interesting. The Goose control block reference. Now, this is where it gets a little confusing. So we need to use the server configuration from the publisher, which we use this. So in this case, we have to type in the name. We'll copy it over. At the end of this goes master / LL in, this is 0 dot GO control block 01. That's the Goose control block reference that you have to put in. Now, the other part that's interesting about this is the data set. You have to put in the name of the data set. So in this case, the name of the data set on the publisher side was this. So we'll just copy this over. So this completes this portion. Then the next thing that we need to look at is we have to indicate what type of signals are populated in that Goose message. These are Booleans, all three of them. So I can do a copy paste. And now the next part is assigning it to a Boolean input so that we can use it for flex logic. So the first thing that we need to do here is we'll give it a name. So I'll keep it simple, something like CIP contact input 1. I have to indicate in the pull down here which Goose message is coming from. We're going at number 1. The location of that contact input is in number 1 of that particular Goose message. I'll go to the second one. This is going to be my virtual input. Once again, it's in the first Goose that we're discussing, but it's in the second location of the data set. And the third one called publisher IOC. Once again, this is in the first data set. And this is in the third position. That's great. That's everything. So now we'll go in and we can save this. The relay will reboot, and then we're going to confirm the communications to make sure that it's working. Okay, the relay is now rebooted. Now we can confirm that the Goose messages are being completed. Let's check for the communication. So the first thing we'll do is under the subscriber side, we'll go into actual values. We'll go into the status screen, and we can check for the status to make sure the communications are working. All Gooses are online. This is good. Next thing we'll look at is we'll look at the signals to confirm that they're changing state. So this is on the subscriber side. So the first thing we'll do is, let me open up the publisher side so we can see what's going on there as well. So on the status, just want to show you the contact inputs and the virtual inputs. So the first one, I'll close the contact input. So this is my publisher, this is my subscriber. Switch it off. Next, we'll control the virtual input. Switch it on. So now we have our second signal turning on. We'll switch it off. Excellent. And then the third signal is our instantaneous overcurrent. So what I've done there is I've just turned the current up. To represent an overcurrent condition. If I remove the current, then the signal goes away as well. All right, that concludes the digital portion of the demo. Next, we'll start with the analog signal. In the second demo, we will configure the two UR relays again. One will now publish two analog signals, VAN and IAN, and the other to subscribe to the analog signals. The signal sources have been configured in advance, so let's begin with the publishing side for the analog portion. Okay, let's go back into the publisher side. So back into the 61850 configuration panel. Okay, and let's go. First thing we'll do is we'll go into the data set. We'll configure the data set. And we're going to give this a different name as opposed to the default. Let's call it feeder underscore pub underscore ds2. And in here we're going to list the analog values that we're going to publish. The first one will be the phase A voltage, VAN. I'll just type it out. mmxu1.mx.phase voltage dot phase A dot cval dot meg dot f. And the second thing we'll look at is the phase A current. Amps dot phase A dot. Okay, so great. So there's the metering for phase A voltage, and the second one, amps phase A. Now we'll come back to the Goose, back to the transmission Goose, the publishing Goose. 1 and 2 are designed for the digital signals, the mission critical signals. Anything with an analog should be going into 3 or 8. So I'm going to select number 3. It's enabled. I'm going to give this a name as well. So we'll call this Goose message feeder underscore pub underscore analog, just so we know what it is. We're going to be using data set number 2. Set up the VLAN, E-type app ID, and then now we can save this. Oh, one moment before we can save it. One of the things that we have to configure here is the deadband on the 2 parameters. So let's go into System Setup. We'll come down into Signal Sources. And this is where we can see our deadbands. Let me just bring this up. So the 2 signals that we're going to deal with are volts phase A. I'm going to drop this down to its lowest number. the amps phase A. All right, so now we'll save it. All right, that completes the publishing side for the analog signal. Now we'll go over to the subscription side. Now we'll take a look at the subscriber side. So going back in, under settings, IEC 61850. Okay, so there's the publisher side. I'm now going to open up the, this is the subscriber side. And I'll open up the publisher side as well, because I need to get some data from it as well. So let me open this up. Okay, I brought this up because we're going to need some information from here as well. Okay, first things first. Under the Goose, subscription Goose, we need to come into the messages. We'll grab the second position. So the first thing it asks for is the Goose ID. So I'm going to come back to the publisher side and grab this information. The name of the goose, the MAC address, the type app ID is 1. Once again, this is this big long phrase that we have to use, so I need to come back into the server for a minute. Feeder pub, followed by master / LLN0.go control block 0. This time it's going to be 3, not 1. So control block 03 this time. The other change that I need to make here is I need to put the name of the data set needs to go in here. That's being published. So I'll come down here. The second data set that we gathered forth was called this. That naming convention now comes down into this field, and now in the field we have to tell the system what type of signals these are. And these are float 32. There's 2 of them. Next, we need to go down to the RX analog inputs. We're finished with this. I'll close that. So we'll come down to the analog inputs. We're going to give this a name. The first one we had was phase A, so VAN. Which goose is it coming from? It's coming in from the second goose that we've assigned. The first location, what the default value is going to be, I'll put in here, I'll leave it at 1,000. And the second device will be IAN. And this will be again from the second Goose, and this is the second member in that Goose message. I'll leave the default at 1000 as well. And now we can save the configuration. Okay. Okay, great. Okay, so let's close this. Now let's confirm that everything is working. Let's come down to the publishing side. And let's take a look at the actual values. Let's make sure that there's 2 gooses being acknowledged. Good. Both online. It means everything's working. So let's confirm the metered values. First I'll bring up what's being published. Here from the metering side, phase currents. And then on the subscriber side, and let me also bring up the voltage as well. So here's my currents, my voltages. This is the publishing side up here. These are what's coming in on the subscriber side. As I vary the current, you can see it reflects across the subscriber side. If I increase the current, it gets transmitted across. Same thing with the voltages. All right, that's great. So that completes our presentation here with version 7.3 and the IEC 61850 configurations. I will stop here and we'll unmute the mics and open it up for a Q&A session. Thank you.